The instruction set of a computer defines a low-level programming language for moving information throughout that computer. In the early 1970s, the prevalent instruction set language used a large vocabulary of different instructions. One justification for a large instruction set was that it would give a programmer more freedom to express the logic of their programs. Many of these instructions were rarely used. Think of your favorite programming language, or your favorite human language for that matter. What percentage of words in the vocabulary do you really need to communicate effectively? We sometimes call these language features syntactic sugar. They add expressivity to a language, but they may not improve functionality or efficiency. These extra language features can have a cost. Dave Patterson and John Hennessy created the Risc architecture, Reduced Instruction Set Compiler architecture. Risc proposed reducing the size of the instruction set so that the important instructions could be optimized for. Programs would become more efficient, easier to analyze, and easier to debug. Dave Patterson's first paper on Risc was rejected. He continued to research the architecture and advocate for it. Eventually, Risc became widely accepted, and Dave eventually won a Turing Award together with John Hennessy. Dave joins the show to talk about his work on Risc and his continued work in computer science research to the present. He's involved in the Berkeley RISE lab and works at Google on the tensor processing unit. Machine learning is an ocean of new scientific breakthroughs and applications that will change our lives. It was inspiring to hear Dave talk about the changing nature of computing, from cloud to security to hardware design. Dave Patterson, welcome to Software Engineering Daily.
Thanks for inviting me.
I want to start by discussing a foundational concept in computer science, which is the instruction set. What is an instruction set?
Well, it's the most important interface between hardware and software. So for software to talk to hardware, it has a vocabulary. And the name of that vocabulary is an instruction set. And the words of that vocabulary are instructions.
If I'm a programmer and I am using a small instruction set in contrast to a large instruction set, how is that going to affect the code that I write, the size of that instruction set?
Well, that's kind of the debate that happened 35 years ago is what's going to be the impact on programmers. Since programmers shifted to writing in high-level languages, starting with Unix, there was kind of no more excuse to write an assembly language. Programs are pretty isolated by that. The technical question was whether these simple fixed-size instructions of the so-called reduced instruction set computers were going to result in bigger programs than the more sophisticated ones. Kind of ended up over the years with a small tweak to the so-called Risc architectures, they'd be about the same code size.
So how does the instruction set affect the speed that a program can be compiled or the efficiency of which that program can be run?
So in terms of compile time, usually compilers are limited by I/O rather than the actual instructions generating. But the big deal, which is what the debate was about, was how much faster it would run. So it turned out for the way we built processors in the 80s that a more sophisticated instruction set, a richer set of $5 words in the vocabulary, wouldn't take as many instructions to execute. Say it would take 3/4 of the instruction of these simpler architectures. But the big deal was that the simpler architectures could read those instructions 5 times faster. So the net win was about a factor of 4 better for the Risc architectures in the 1980s.
How does the size of an instruction set affect the debugging process for a programmer?
Yeah, let me just put a qualification here. It isn't so much the size of the instruction set as how simple the instructions are themselves. So if you think about it as a vocabulary, the debate was kind of these big polysyllabic words versus very simple words. So the reduced meant kind of simple words as well as kind of possibly fewer instructions.
I'm really glad you pointed that out because I think one example that I heard you gave, I was watching some talks you gave recently, there was something like a polynomial simplification instruction that was very rarely used. You gave it as an example where it's a very complex instruction and it's rarely used, so you don't necessarily need that in your instruction set.
Right. what actually happened, going back to the 1960s, is they simplified the design of computers by kind of building an interpreter inside the computer, and we called that interpreter a microprogram. And what was one of the cool things about the microprogram is it was really easy to add very sophisticated words to the vocabulary, very sophisticated instructions, such as polynomial evaluation. So it didn't take a lot of hardware to add that kind of cool instruction, but it turned out that it was almost never executed, right? So if we needed polynomial evaluation all the time, it would have been useful, but it wasn't useful because it was hardly ever executed. So it was extra cost to provide that sophistication that didn't result in all that much benefit. So that led to this kind of reactionary movement of the Risc architectures that fundamentally what they did is they got rid of that little interpreter inside the computer, the little microprograms. We made those go away, and software went directly to the hardware, which got performance advantages.
So back in 1979, you were an academic. You were getting your PhD at Berkeley.
Nope.
And
let's see. I graduated in 1976 from UCLA with my PhD, and by then I was a professor at Berkeley in 79.
Got it. So I know that at some point you took a break from academia to work at DEC, and that was when you saw...
Yeah, it was the fall of 79, right? I took a leave of absence from Berkeley to do an industrial leave to help DEC with bugs in microprograms.
Right. So when you saw these issues with microprogramming that were in existence in industry at DEC, were these things that academia was unaware of?
I think they were unaware of how buggy it was. That's why they brought me in. It was a lot of work to get these microprograms right. And, it made sense for the type of computers that DEC was building, the mini computers, which consisted of thousands of chips. But kind of what struck me is when I came back from sabbatical, and during the sabbatical, is what's going to happen if the microprocessor guys follow the mini computer guys in these kind of sophisticated instruction sets? Given all the bugs I was seeing in these mini computers, what are we going to do with microprocessors if they also get so sophisticated that with these giant microprograms that could be buggy?
And so when you came back to Berkeley with that observation from your time at DEC, you wrote a paper that proposed a computer architecture that was optimized for a smaller number of frequently used instructions. Is that correct?
Well, if you want to get, I don't know if the full history matters, but I actually wrote a paper saying, hey, we're going to have to build microprocessors that allow you to repair microcode. And the ironic thing is that paper was rejected because the reviewers felt it was a stupid way to design computers is to have microprocessors that had to be repaired in the field. So because that paper was rejected, that led me to start thinking about architectures that didn't have those microcode interpreters for microprocessors, and that was the Risc architecture work.
Now, did you doubt your ideas when they were rejected, or did you just feel like you had to reframe similar ideas in perhaps a different wording or a different paper?
It wasn't... I was sure I was right, and in fact, historically, I was right. Is Intel, which the x86 architecture, which does have a lot of microcode, eventually did put microcode repair mechanisms. The thing that got me thinking was that the reviewers thought having instruction sets that were so complicated that they had microcode bugs wasn't a wise instruction set for microprocessors. And so I kind of, in my mind, I had two facts. Like, if you build sophisticated instruction sets, it's going to have bugs that you have to repair. Microprocessors that have to have bugs repaired in them in microcode are not such a great idea. So what do we do next? And that led to the proposal of simplifying the instruction set so we didn't need the microcode interpreter. And then the questions were, well, how many more instructions would you have to execute if they were simple? And how much faster could you read them if they were simple? And that took a couple of years to figure out. Many
of the best ideas in science can seem heretical at first, and they can get misunderstood initially. Actually, I'm just thinking about this. I interviewed Leslie Lamport one time, and I think his first paper on distributed systems, the Paxos paper, was rejected by ACM, I believe, and then he reformatted his ideas or rephrased them and he got them accepted and became kind of the father of distributed systems. How should a computer scientist react when they get their ideas rejected?
How should they react? Well, it's a common story. Kind of the problem is when you're younger, you don't quite understand how the reviewing system works. But basically, in a reviewing system, if you're speaking gospel in the paper, it's easier for people to evaluate your ideas, and they're more acceptable. And in a reviewing system, like there's 5 people, say, reviewing your paper, when what you're proposing is contrary to conventional wisdom, it's going to take an enlightened reviewer to be able to see the value of that. And a common reaction in a reviewing system will be several of the reviewers won't get it and think it's the wrong thing to do. So it's a pretty common thing with somebody who's got a big idea for them to be rejected. I think Tim Berners-Lee too says his first paper on World Wide Web was rejected by the World Wide Web Conference, basically. So it's a common reaction. And a Turing Award winner, Jim Gray, said the same things. All his best known results were rejected the first time, but all his follow-on papers were accepted. So it's kind of a standard. So what should a computer scientist do? If you believe in what you're doing, you shouldn't be discouraged by a rejection, because you could, if it's a big idea, you could be in good company.
You wrote a textbook called Computer Architecture: A Quantitative Approach. This is a textbook that's in wide use. Was that an attempt to quantify some of those ideas that had been subjectively evaluated by that review committee that ended up rejecting them early on?
It's a little more than that. So the 2 academics who led the Risc effort were John Hennessy at Stanford and I, and we shared the Turing Award for that. So what it captured is, at the time, is computer architecture was often done kind of based on experience and intuition. It wasn't so quantitative. So in teaching that material at Stanford and Berkeley, it was pretty dissatisfying to use the textbooks which describe, here's computer X, look, here's the list of features it has. Computer Y, in contrast, has these other features. And, and it basically, you're supposed to kind of absorb all prior designs, and then when you got a chance, you'd use your gut to come up with what you think is a good design. So and not only was it bad in the classroom, I think it was bad engineering to do things that way. Kind of the reason it happens is just the pressures to get something done in a company then and even now is, well, if we take a year to figure out what to build, that's a year that we could be building something. So there's urgency to get started, and then people can skip the step where they investigate the ideas. So John and I decided we were frustrated by it, and then by the end of the decade of the 1980s, once the Risc ideas were starting to catch on commercially, we decided it's time to write a book that would try and capture kind of the way we were building things, which had a more quantitative approach. And we were definitely driven by taking this kind of catalog description of computers into something where there were formulas and experiments you could run to decide if computer A or approach A would be better than approach B.
You're now spending a lot of time on machine learning applications, specifically the chip design for machine learning applications. How quantitative is the evaluation of deep learning architectures, I guess, on the software and on the hardware side these days?
Well, to me, it's like reliving my history. I kind of feel like I was, a professor at Berkeley for 40 years, and then I retired, but have started working part-time at Google. But I feel like I'm repeating my history here in the machine learning. So one of the big problems in the early days of computer architecture was the lack of good benchmarks. And so what happened in the 1980s is there's this effort called SPEC, which was a consortium of companies in the Unix marketplace that got together to agree on standard benchmarks that they would all run so that everybody would agree how fast something was. Before there were standard benchmarks, they'd have companies like HP versus companies like Sun, and they would argue, well, my computer's a 10 MIPS computer, and those guys are liars. They say they're 10, but they're really 9. So that didn't do much for the marketplace when the customers were told we're good, but all the other guys are idiots. And so the Unix community got together and agreed on a standard set of benchmarks, which was called Spec, which they've refreshed every few years in the last 25 or 30 years. And so once there were standard benchmarks, led to all kinds of great things that inside of companies, they could prioritize what's the right products to build. Academics had benchmarks that they could use to come up with new ideas. Compiler people could tune their architectures to these compilers. So if you have a good set of benchmarks, it kind of accelerates progress in the field, frankly. So come to machine learning, and Google's building hardware, NVIDIA's building hardware, Microsoft has ideas there, but there was only trivial programs that everybody would run, and even when they had the same name, it wasn't necessarily exactly the same program with exactly the same data set. So it was back to the bad old days. As a result of that, a group of us, repeating history, have decided to do a standard set of benchmarks for machine learning. And the name of this effort is MLPerf, P-E-R-F. And it's a particularly exciting time right now, is the first deadline for MLPerf is I think 10 days from today. Everybody's going to turn in the results who's going to participate on November 9th. And then after some number of weeks of checking the results, by the end of November, we'll release the results, but we'll see fair head-to-head comparisons between Google and NVIDIA and Intel, and I don't know how many people are going to participate, but it's sure to be an eye-opening set of results when they hit the surface.
I think I want to come back to machine learning a little bit later. On the Risc front, your ideas were eventually validated. Risc became widely used. It changed the world. You won a Turing Award. In retrospect, when you think about the path that you took to developing Risc, was that deliberate? Were you looking for a world-changing idea, or were you simply studying what was interesting to you and you stumbled upon this insight?
Well, when I joined Berkeley as a new faculty member just after getting my PhD, they told me what Berkeley wants to do is have positive impact in the world. We don't count papers, we count impact. I loved that advice. That's what I wanted to hear. And so I took that to heart. And so we wanted to, in baseball terms, we're not bunting for singles, we're swinging for the fences. So we were trying to do big things. And we thought our ideas made more sense for microprocessors. Maybe for mainframe computers and for mini computers, these rich instruction sets with microcode interpreters were a good match, but they weren't a good match for microprocessors, which were changing fast with Moore's law. We wanted a simpler architecture that could track the technology. So we thought our ideas were better ideas, and we thought if we were right, that basically all microprocessors in the world would use them. And we believed in Moore's law, so we thought microprocessors were the future of the computing industry. At the time, mini computers and mainframes dominated, but we thought, Moore's law was going to put microprocessors front and center in the computer industry. So we expected this to have a giant impact and to work well, but that was us in the ivory tower making these arguments, and we had to see whether industry was going to follow.
Since that time, you've continued to do research and development involving both academia and industry. You were part of the Berkeley AMP Lab, which led to creations of companies like Spark, projects like Spark and Mesos and Tachyon, and each of those have become companies, or in some cases multiple companies have come out of them. This lab was active from 2008 to 2017. When you think back about that period of time, 2008 to 2017, what were the fundamental problems that the AMP Lab was trying to tackle?
Well, it was actually some of those things got started in the lab before that, which was called the RAB Lab, and which is the lab I led, and then the AMP Lab continued with those ideas. So Spark and Mesos started at the end of the RAD Lab and went forward for historical accuracy. We were trying to make it easy to create next great internet services in the RAD Lab, and we thought brought together machine learning people. Mike Jordan, my joke is Mike Jordan is the Mike Jordan of machine learning, and he was involved in the beginning, and Spark actually got started with machine learning people getting frustrated trying to build do machine learning using systems like MapReduce in the cloud. It was clear the cloud was the future. We were all in on the cloud, but the software to do machine learning on the cloud was just didn't work well. It was really hard to do. So that problem inspired Matei Zaharia and others to develop Spark to make it much easier to do machine learning, and then it Spark does a lot of things besides being machine learning in the cloud. So I think that's the historical setting that led to these innovations. And then Mesos, what's it mean to have an operating system for the cloud? That was another kind of opportunity that was clear if you believed that the cloud was the future of the computing industry.
Matei still feels that machine learning is too hard. The APIs or the application layer that a programmer has access to are still too difficult to operate relative to the gains that you can get from programming machine learning applications. What needs to happen to make machine learning more accessible?
That's a great question. Matei, by the way, is also involved in the ML-Perf effort that I mentioned. But it's interesting, I've seen a few technological revolutions in my lifetime. And what's different about machine learning is it seems to have very high impact and certainly commercial value, but it's hard to learn how to do. It feels like more of an apprenticeship program that you have to be near some of the great centers to figure this out rather than you just pick up a book and start using it. People are building lots of software stacks that claim to make machine learning much easier to do, but it remains, a technology that's not easy to learn. The learning curve is pretty steep. So I don't think it's only the software stack. It's something about the technology itself that is hard to apply.
Since the AMP Lab has, closed, it evolved. It evolved into the RISE Lab. So you are now part of the RISE Lab. That stands for Real-Time, Intelligent, Secure, Explainable Systems. One tagline from that is technologies that enable applications to make low latency decisions on live data with strong security. So that idea of low latency decision making on live data with strong security, is there a fundamental trade-off between the latency of a system and the security of a system?
I don't know if that's true as much as a lot of research projects have ignored security. I would say, we could have there's no reason security couldn't have been a focus of the RAD Lab or the AMP Lab. It would have fit in there. It's just when you do a research project, the style we do it at Berkeley is we pick these 5-year research projects. And the reason they last about 5 years is it kind of matches how long graduate students are here before they graduate. And also we believe, it's a fast-moving field, and it's hard to predict the future, more than 7 or 8 years in advance. It's hard enough. And so every 5 years we want to give ourselves a new shot to see where we think where the goalposts are. So I'd say we think, given what happened in the industry, that the RAD Lab and AMP Lab helped happen in the industry, that the next set of challenges were around live data rather than batch processing and really quick decisions. And then, security is just so embarrassingly terrible. And there's some hope that with more flexibility with hardware support and ideas like enclaves, that maybe we could make some progress on this problem. The other side of it is, if we're really going to deploy this technology and it's going to make quick decisions, there's going to be a lot of private data involved in that, and we need to protect it. So I think some combination of the opportunity and the need has the reason we brought security in there. But it's been a big problem for a long time.
You used a term enclave. What is an enclave?
It's a phrase that Intel popularized. I believe it means to have a protected area where, kind of like the trust zone, but it's a protected area. Only the software inside of that protected area can get access to pieces of information. So not even the operating system can get access to things that are protected. So you try and keep everything, encrypted so that not even the operating system can access it, but it's just inside the enclave you can do that. And the hope is by having a small area that you have to trust, that'll lead to more secure systems. So Intel's name for their enclave technology is SGX. But there's a bunch of people hopeful that this type of technology will let us make some progress in security.
When you're looking at the technologies in the Rise Lab or the projects and the people that you've talked to, are there any solutions that you're particularly optimistic about? Because I've been covering some shows around this topic, like Bruce Schneier, for example, has been talking about the dangers of connected cars and sensors and the smart power grid, and this is like the same infrastructure that we would love to modernize. We would love to have machine learning be optimizing our power grid like it's optimizing Google's data centers. But the more we do that, the more we're exposing those areas to smart systems, networking issues that could expose them to hackers or just erroneously architected machine learning models. What's the solution here, or what kinds of promising solutions have you seen in the Rise Lab?
I agree. It seems like opening this up is opening a can of worms, or maybe that's not scary enough, a can of snakes. So I think partly there's some ideas that gives one hope, but it's also, I think it's the process. So early on in computer architecture, there are some protection mechanisms in the hardware that made things more secure, like 30 years ago. But the operating systems of the time didn't use them. They were less concerned about security probably and more about ease of use. And they were somewhat expensive to have, these protection mechanisms, so they kind of atrophied and fell off, and they went away. And maybe the hope was software, maybe through formal program verification, was going to make things secure, but clearly that hasn't happened. So I think partly the reason for the Rise Lab is the recognition that if we're going to make progress in security, hardware is going to have to help. And I don't think we're going to get there without changes to hardware. So one of the things we're excited about that came out of one of the other labs at Berkeley is this idea of an open architecture. And this particular one's called Risc for the fifth Risc project at Berkeley, but it's an open architecture. You can think of it somewhat like Linux is an open operating system that is industrial strength. It can run, has a real software stack, runs real apps, but everybody can use it. And why this might be exciting for security is you could run a version of Risc, not fast, but fast enough to run software on what's called a field programmable gate array. So this is kind of pliable hardware that's slow, but you can change every day, every hour. So the hope is you'd put a Risc architecture idea out there with whatever your security ideas are built into this kind of pliable hardware, and you could subject it to attacks. So for me as an outsider for security, I see people criticizing things. I would say, oh, look, Microsoft, you've got bugs, or look, Oracle, you have bugs. But they aren't synthesizing. They aren't creating artifacts that they claim is secure and test them by seeing if people can attack them and whether they can defend those attacks. I think the Risc technology makes it possible for anybody who has a great idea, not just people who work for ARM or Intel, but anybody, to get one of these, modify it with their ideas, and put it out on the internet and see if it survives attack. So it's kind of, the argument is not some breakthrough idea, but a new process, a new approach to let us test ideas of security so that we can make progress on this problem.
You're now working on TPUs at Google in some of your time. So this is a domain-specific chip architecture for machine learning. That's what a TPU is, tensor processing unit. Why do we need domain-specific chip architectures for machine learning?
Yep, great question. Because software people shouldn't like this, right? Is special purpose architectures that are going to get more heterogeneous. How come we can't just keep buying Intel processors and make our software stack go faster? Well, those were the good old days. Basically what's happening, there's the end of Moore's law, so the number of transistors per chip isn't doubling every year or two like it used to. There's a lesser known fact called Dennard Scaling, which is, a question you should have been asking is if you can double the number of transistors per chip every year and those transistors are using electricity, why aren't our chips burning up? And Dennard observed is what happened is that we lowered the voltage that distinguished between the 0 and 1 every time we made the transistors smaller. So actually, in a square millimeter, the power remained the same despite having more transistors, so it got more energy efficient. Well, about 5 or 8 years ago, Dennard Scaling stopped working, and so the power per chip went up. So the combination end of Moore's law and the power going up per chip means performance has plateaued. Nobody has a great idea of how to secretly, under the covers, make general purpose processors run faster, like Intel builds. So in Hennessy's in my textbook, the first figure plots the improvement in performance annually. And what's happened over the 6 editions, it's gotten flatter and flatter. And in this last year, it went only up 3%. So that's doubling every 20 years. So if you're a programmer and you're sitting there waiting to buy the next Intel processor to make your software go faster, you're going to have to wait a long time. So what's left? What's left is, as far as all architects, and John and I think this, is not general purpose. So we'll find an important area, build hardware for that thing only, and see if you can accelerate that piece. The rest of it, you won't worry about, but the piece you care about, you can try and get big factors of performance improvement.
Of course, machine learning itself is a broad area, and I believe that today the TPU is used for all kinds of machine learning applications. Are we going to need more specific versions of machine learning chips?
No, I think machine learning is a very exciting area for a bunch of reasons. One of it, it's just ignoring the architecture stuff. It's an exciting area, right? You've heard these stories about the main conference. 2 years ago, it sold out, after 3 months, and last year it was 1 month, and this year it was 11 minutes, right? So there's huge interest in machine learning. But machine learning at its heart right now is got pretty simple computation models of basically so-called tensors or two-dimensional arrays or three-dimensional arrays computing. So matrix multiply is a big piece of what the machine learning is about. That's music to architects' ears. Matrix multiply. Well, we know how to make that go fast. So what's exciting from an architect's perspective about machine learning, here's a very important area that is pretty widely applicable. People are trying machine learning all across the industry, but at its heart, the computation model is relatively simple. So that's an exciting thread that's going on. And the TPU, Google's had 3 versions. The first version of the TPU, which was done in 2015, deployed in 2015. If you use Google, use it every day, and they've announced 2 more versions of it. And this is a very exciting area, what's going on right now. I'd say it may get more specialized. One example of that specialization for machine learning, there's really 2 phases. There's the learning, where you're training the neurons to do what you want them to do, and then there's after they've learned or after they've been trained, you want it to start doing stuff, predicting it, and that's sometimes called training and inference. So certainly, particularly for embedded devices, inference is what you want. Typically, you're going to train it in the cloud, but inference would be in all kinds of gadgets, phones, all kinds of sensors are going to have inference things in them. So there'll be that separation for sure. But in general, the architectures are probably similar. Although, if you look one layer deeper, these companies all have different bets. So Google is building really big, powerful multipliers. NVIDIA has thousands of threads. Microsoft is betting on field programmable gate arrays that you program themselves. So we're seeing kind of a Cambrian explosion of architectures of different attacks on machine learning. Not that it's fundamental, just everybody's got their own opinion and the right way to go, and we're going to see some exciting progress.
Now with inference, you can have these issues where you need to parallelize training of a model across a gigantic data set, or you might end up having a model that's so big that you have to break up the model into multiple machines, and then so that's during the training process.
During training, right?
During training, I might have said inference accidentally. So that's the training process. And then during inference, you might have some latency guarantees that you need to fulfill, and other constraints in the inference process as well. So do we need domain-specific architectures for like the systems that are consuming the models, and then other domain-specific architectures for the ones that are training the models?
Certainly if you train, you can also do inference. But it does make sense to have inference-only chips, particularly, like I said, for battery-operated devices or things in the field. It's not clear that you have enough data to do all the training. There's some people who think there's opportunities there, but conventional wisdom is in the field you're doing inference. Often you're doing it on small devices, so special, very low-power devices aimed at inference, there's a huge market for that. In the cloud, you've got a lot more power and a lot more cooling, so you can have bigger, more powerful systems. Google has announced besides 3 generations of chips, they've announced 2 basically supercomputers. The first one has a peak performance of about 11 petaflops. That's TPU version 2 in what they call a pod, which has 256 chips. And then version 3, their pod announced as 100 petaflops. And so what do these numbers mean? Well, if you use one of the measures for supercomputer performance, and this is different kind of floating point operations, those are bigger operations, but nevertheless, 100 petaflops is the 3rd fastest computer in the world using the top 500 measures. So these are amazingly powerful computers that are being constructed, and these are being constructed to do the training phase of machine learning.
I think a lot of the applications that we look at for machine learning today, a batching process works fine. Like if you're training a machine learning model to do image recognition, that's fine if you just batch all the images in and then you deploy the model and the model can run wherever. But if you were doing something like monitoring somebody's health, and you at every 5-second interval you want to retrain the model on the most recent health parameters, then you would need a much more tighter physical coupling or at least lower latency between the training process and the deployment process. Has there been much work around the software architectures we need for more streaming, lower latency, tighter feedback loop between the training and inference process, or are we mostly kind of in a time where we think about these things as highly decoupled processes, the training versus the inference?
Let me qualify. I'm not a machine learning expert here. I think the example you gave, though, you wouldn't be using a patient's live data to train it, because medical software has to be very carefully certified and stuff like that. So you probably have a trained model monitoring a patient, and then you'd be caring about low latency, about as it found features that are worrisome, you'd want it to very quickly recognize it. There are machine learning leaders who think this separation of training and inference, these two worlds, is a temporary situation. If we're really going to make big progress in machine learning, systems should be training all the time and inferring all the time. That those will go back together. But you should be talking to machine learning experts about that, not me.
Okay. Can we impose latency constraints on ML inference today, or do we have highly... Okay, we do.
Yeah, I mean, at Google, the paper that we wrote about TPU version 1, we pointed out that this was an early effort, and at Google, engineers talked to the internal customers and said, do you have any latency demands? And most of them said no, and the ones that did said 10 milliseconds, I think, at the time, or 15 milliseconds. Well, then when the hardware was built and deployed, they said, of course, our latency demand is 7 milliseconds, which was kind of startling to the hardware designers. Fortunately, they had a design that worked pretty well at low latency. But I think one of the surprises in that first paper was that even in a data center, response time is king. And so one of the reasons the TPU version 1 did better than the GPUs and CPUs of the time is they weren't as good under low latency constraints. Kind of typically for most computer designers, they worry about the average case rather than the worst case. And fortunately, the way the TPU was designed, its worst case was much closer to its average case than a typical computer. So this kind of what's called tail latency for inference is important, that people care about the 95th percentile or the 99th percentile in these apps that we use every day, because a lot of inference apps are dealing with a human being, and response time is very important for human beings. So one of the things that I mentioned, this ML perf thing that's happening, the first thing they're doing is training, but later they're going to go after inference, and they're going to have to agree upon what's the latency bounds that make sense for these benchmarks. But the measure is going to be milliseconds. So it's tight timelines are going to be fundamental to inference technology.
Tell me more about the ML perf characteristics. How do you evaluate the performance of a machine learning system?
It's kind of, if you're a researcher, this is very exciting because it's a wide open and it's unclear what the right answer is. If you're in a company trying to make money, it's scary, right? So part of this consortium of a lot of companies and universities working together is to figure this out. We decided what makes sense to do for training is the performance piece of it is time to train something up to an acceptable quality level, a quality score. So, what percentage of the images do you miss, right? Or what percentage do you get right? And then how long does it take to train that? So that's one part of it. The other parts that we wanted to do is to to take advantage of the fact, are we talking about a chip that's in the laptop or 200 chips in the data center? How are we going to have a scale factor? We're going to go with two things. Since a lot of people use the cloud and there's an economic system in the cloud, we're going to provide relative cloud costs if you're using a cloud version of it. And the other thing we're going to do, although it's not going to be ready for what we call 0.5, is record the power that you use. So if you're using a really big system with hundreds of chips, that's going to use a lot more power. And so you'll be able to see how big a system we're dealing with. So time to train, cloud costs, power use are going to be the key factors there. And then later they'll do the inference ones, but they'll factor in cloud costs and power as well, I think.
How does the overall resource consumption of machine learning, both in terms of inference and training, how does it compare to other workloads in a data center?
You mean the fraction of it, or just how does it behave? Or
well, in terms of it, as an example, when a company like Google is looking at what is taking up an increasing volume or increasing share of resources, and what they're looking at, we need to provision, or we need to build more data centers for these kinds of purposes. Like, in what categories are the machine learning workloads taking up an increasing volume of resources? Or I guess I'm just curious how the growing, because I know that machine learning workloads are growing. I don't know if they're growing in parity with other kinds of workloads, or if they're dwarfing the other workloads.
Well, yeah, there's a paper that was done by this group at OpenAI, and they talked about kind of the bleeding edge of machine learning. How rapidly are they absorbing or needing computing cycles? And they measured it is going up by a factor of 10 each year. So Moore's law is a factor of 1.5 or 2 every year. They're saying they plotted a bunch of people's results at OpenAI and Google and elsewhere, and saw at the leading edge they could consume as much as we could build. So if you're like me and a computer designer, you love people like this. You hate people say, my computer's fast enough. I don't know why you're trying to build faster processors. Those aren't your friends, right? You want people like, I can't get my work done. If you gave me 10 times as much, I know immediately what I do with it, and I could do great things. And so it appears that certainly the training phase of machine learning, that the faster, bigger that we can build them, they're going to put them to good use. So it's an exciting area there. Now, the story of how Google got into this was like 2014, I think it was Jeff Dean said, well, look, if machine learning catches on and all of our customers start doing machine learning and we run the machine learning on the CPUs at the time, we're going to have to double the number of the data centers. And that was kind of oh my God, we better do custom hardware, because otherwise we can't afford to double the data center. So that was kind of the initial point that led to this. And then what happened, I think, in the industry is when Google in 2016 announced, by the way, we've decided to build our own chips for machine learning, and they're 10 times better than everything else. That got a lot of people's attention, and then kind of led to people at other companies doing their efforts, and startups and all kinds of things going on. So it's perceived that machine learning will be a much larger share of the workloads in the future, but people are trying to guess that. And there's papers that indicate that if you gave them much bigger computers, they'd know what to do with them.
As you've gone from TPU version 1, I think you're now on version 3, is that right?
Yes.
What has changed in that iterative process? How has the hardware architecture evolved?
So there's not a lot of details that Google's released yet. We're working on a paper for TPU version 2, and we hope the program committees will accept that paper. But fundamentally, version 1 was for inference only, and versions 2 and 3 are for training. Revealed some details about it. One of the details is there's this thing called the IEEE floating point standard, which started at Berkeley, which led to a colleague of mine getting a Turing Award, and everybody's followed that for 30 years, right? That Google said, the IEEE standard and floating point has the wrong balance of what's called the exponent and the mantissa. We should change that. And they changed it going against the standard because that's better for machine learning, which is kind of scary things for computer architects, but it's much more efficient and it's easier for programmers and things like that. There's been this argument all a long time that numerical accuracy isn't as important in machine learning given the types of things it's doing, and Google's taken advantage of that in one of these chips, and it's one of the advantages that these chips are using to deliver the performance they're after.
Do you have any reason to believe that there might be certain applications where higher degrees of precision are going to be important?
Yeah, I mean, this is, what's unusual about this is tremendous excitement in the architecture community about machine learning. But if I think about that in the 80s, the software stack was pretty stable, right? The applications weren't changing left, right? But in machine learning, it's things are moving at light speed, right? So it's changing fast as well. So I think what architects will tend to do is put in both optimized narrower data, but continue to support the wider data, and then it'll be up to software to see when they can take advantage of it. What our paper talks about is a bunch of production applications that we use at Google today can take advantage of the narrow data type, but we still support the wider data types. And where the field will go is one of those things that make life interesting for architects. You have to try and guess where the field's going to be in a few years because your chip lasts a long time. And are you going to be right, or did you leave something out? And that makes you wake up every day with interesting things to do.
When I talk to researchers in different areas of computer science, I sometimes feel like there's kind of two modes. There's this one mode where you're beating your head against the wall of this one problem. You're just trying to figure it out. You're so stuck. And there's this other mode where you just feel like you're in a blue ocean and there's more interesting problems and stuff to revisit and examine than you could ever possibly get to. Do you feel like machine learning is in either of those particular categories?
Good insight. Yeah, I feel like I would have said it slightly differently. I'd say there's times from a research perspective where things are pretty boring. Industry's very happy what they're doing. They do the same thing every year, and what they're going to do next year is going to be fine, and they'll make lots of money. And then if you've got a new idea, it's really hard to get their attention. And there's other times when it's chaos, and it's unclear what's the right way to go. And there's all kinds of problems that nobody knows the answer to that if you could figure out the answer to, they would love to embrace those ideas. And that's where we are now. In machine learning, it's, there's all these companies are making very different bets, wide variety of heterogeneous architectures, and there's lots of good ideas out there, but it's not clear which is the most important idea. So there's plenty of problems at the hardware-software interface of machine learning for people to study. Google's hiring, right? we would love to get more help to investigate these ideas. There's lots of people working on it. So I think we're just going to see this, when Hennessy and I talked about this, we called it a golden age. We think this next decade is going to be a golden age in computer architecture with tremendous opportunity for impact, a tremendous opportunity for innovation. And that applies to machine learning as well as the architecture things.
You've said that a key to your success is doing one big thing at a time throughout your career. That said, there are places, like if somebody looked at your career, they would say, okay, he's done industry and academia at the same time, or he's like spending 2 days at Google and 3 days at the Rise Lab. This sounds like he's doing multiple things at once.
Oh, yeah, qualify that. Yeah, then what I think it was, I woke up and it was like God spoke to me, do one big thing at a time. I do other things. So I'm spending a day a week at the Rise Lab helping them. We're actually working on a Berkeley view of serverless computing, which is an exciting area to work on, and I'm helping with that. The big thing I'm doing now is helping Google with, future TPU. That's the big thing I'm doing. So I try and I've kind of, per year, I do one big thing. There's been times where, like, I think last year there's this open architecture Risc 5, and a colleague and I wrote a book on that. So that was the big thing I did the prior year. So I try and do one big thing a year, but it's kind of more narrowly focused on a project rather than am I spending some time at a couple of places. I'm helping out wherever I can, but the big effort is around future hardware for machine learning.
Well, I know we're out of time, but if you have any suggestions for who to talk to about that serverless effort, I would love to talk to somebody about that.
Oh, sure. We're finishing a draft on it, and we think serverless is the future of cloud computing. And, there's some challenges that have to be addressed, but it's a really interesting, exciting area. There may be some opportunities to make the security issues better. But yeah, I'd talk to Jan.
Yeah. New schedulers?
Yeah, he cares. He's got ideas about that too.
Okay, great. Well, Dave, thanks for coming on the show. It's been a great pleasure talking to you.
Okay, well, thanks for inviting me.
Wow.